What's up, guys? This is Aminowitz, and today this is my Physics 2212 Lab 4 circuits. So introduction is our objective here is to create and observe various physical series and parallel RC circuits. In doing this, we hope to observe the loop rule, the idea of a steady state current, as well as charge conservation through the usage of multimeters and specifically ammeters, and compare our experimental physical circuits to the predicted values that we calculate or expect from a virtual circuit. And our results preview is for a series circuit, our calculated current came out to be 0.02 amps. So now we're going to go through what the difference between a series and parallel circuit is. So a series circuit, as seen on the left side, is where all resistors follow the exact same loop. So only one loop is present, and to get your resistance across the entire thing, R total is R the first one, which is seen right here, plus R the second, plus R the third, up to any nth power of resistors. However, in parallel, you can see there's multiple loops. You got one loop right here, one loop right here, one loop right here, one loop right here, and a loop right here. So that's what makes them different, is you can see, think of it as they're running legit in parallel. And to get the resistance from this one, it's R over your R total is equal to 1 over R1 plus 1 over R2 plus 1 over Rm for any number of resistors over an infinitely long wire. Some key concepts here are the loop rule is the sum of the current entering a junction must equal the sum of the current exiting the junction, or current in equals current out, and follows conservation of charge. The node rule is the difference in electric potential for all closed loops in a circuit must be equal to 0, where delta V1 plus delta V2 plus delta Vn equals 0. And this is conservation of energy. A steady state circuit is a circuit where the charge and current is 0 for constant flow of current. The charge drift speed is constant, and there is a constant non-zero E field inside of the conducting wire. And voltage across the capacitor is calculated to be V equals Q over C. Voltage across the resistor is calculated to be V equals IR. And remember those equations because we're going to derive them later to solve for some values. A symbol for a capacitor is seen right here on the left, which is a wire and then two equally sized spaced apart plates. And resistor is this little heartbeat looking symbol. So the first part, we made a series circuit, and our system is a series circuit consisting of battery, wires, light bulb, and capacitors, as well as two ammeters. And the lab shifted from online to in-person, which caused some confusion. So this is our circuit, but we ended up swapping the battery for the proper two batteries because we misread it the first time, and we plugged our ammeters in right here and right here, connected to the capacitor and the bulb. So the two batteries are a total of 3 volts. Our resistors are 47 ohms and 100 ohms each for a total of 147 ohms because you just add them because they're in series as shown earlier. And we have two ammeters to measure current at both points, which the resistance of this is theoretically 0, as we want it to be as low as possible to avoid adding to our R total. And our results from this were our measured values at both points for I1 and I2 should be the exact same, which is V over R derived from our V equals IR equation, where our expected current is 0.20408 amps. However, with the ammeter, our measured value at both points was 0.02 amps. When we flip the ammeter, the direction of our current measurement flips, which effectively, in the eyes of our ammeter, flips the direction of the current itself. So our current becomes negative as negative 0.02 amps. For our potential differences, at the battery, we have an expected value of 3 volts, at the wires of 0 volts, at the 47 ohm resistor of negative 0.959 volts, and at the 100 ohm resistor an expected value of negative 2.041 volts. As you can see, these all sum to 0. However, in reality, wires have some resistance, which throws our values off slightly. Our experimental value is 2.99 volts. For the wires is negative 0.0024 volts. The resistor is negative 0.964 volts, and our 100 ohm is negative 2.043 volts, which still, however, adds up to 0. And finally, our resistances at each wire come out to be, at the wires is negative 0.12 ohms, which makes in reality our 47 ohm resistor have 48.2 ohms of resistance, and our 100 ohm resistor have 102.15 ohms of resistance in reality. For part 2, we created a RC, which stands for resistor capacitor circuit. So in this case, the circuit was the exact same as last time, but a capacitor is inserted in as well. And they will also observe the charging effect of a capacitor through the light bulb plug-in. So just like in the first circuit, the light bulb does light up, but it begins to dim over time due to the charging of the capacitor. So what this means essentially is when first connected, charges from one current jump from one side of the capacitor to the other, completing the circuit, which is like the gap we saw in the logo. However, once both sides are balanced, the circuit breaks and the capacitor no longer charges, which means current is no longer flowing, which causes the light bulb to dim over time and eventually turn off. And so this can be graphed right here in our ln V over V naught versus time graph, which is this linear slope right here. And the slope of the graph is evaluated to be roughly 6 seconds. And this is called our RC time constant. It's important to know as well that charging and discharging times for the capacitor are roughly identical in the series circuit. But when the resistor is added, they both increase by around the same amount. Finally, the what-if questions. If this lab was done, so we were supposed to assume this lab was virtual, but since we did it in real life, in reality, ammeters do not have a resistance value when you use it in an experimental online circuit, but in real life, they do not have that value of 0. So as a result, our resistances observed at each location were slightly different than it would be in a virtual counterpart, due to the ammeters having a tiny bit of resistance as well. Secondly, what if this lab was done in real life, which it was, and an actual battery was used to charge a real capacitor with no resistance? How quickly would the ideal model predict the capacitor to reach full charge? Using ammeter to learn how long it would take to charge. And so virtually, it would be, if we use a virtual lab, it would be faster than our real life calculation, because the capacitor takes less time to charge virtually, as their ammeters and wires are assumed to have no resistance. But in real life, they have a slight amount of resistance, which causes the charging time to be slightly increased. Thank you so much, and have a great night.